Welcome guys, today I'm going to be proving the divisibility of this expression on board, but not using the usual modular arithmetic way. Instead, we're going to do it using the principle of induction. And for certain expressions, this works actually very well, as you're about to see. If you think you have a solution using modular arithmetic, please leave it below in the comments. I'd be very interested to look at it, because I think it's actually quite difficult. All right, let's get started. First, we need a base case for induction. As always, here we have to prove that this expression is true for all n in the naturals. So we can just pick the smallest one as 1. We get 3 to the 3 times 1 plus 3, minus 26 times 1 minus 27. We have to say that we have to show that it's divisible by 169, as seen. And I'm going to spare you the calculation. This is going to be 676, which is in fact equals to 4 times 169. So our base case holds true. Now we just have to show that this expression works for the condition of n plus 1. So we're going to first take a note here. It's not that difficult of a note. We're just going to move around this expression to isolate 3 to the 3n plus 3. It's going to equal 169m minus 26n minus 20, plus 26n and plus 27. There we go. That's what we have to know, and that's what we're going to use in the induction step. Remember that now we assume that this statement is true. We have to show that it is true for the case of k plus 1, some arbitrary number, natural number k. We have 3 to the power of 3k plus 1 plus 3 minus 26k plus 1 minus 27. And it has to be equal to 169 times some integer L, let's say. This is what we have to show using our hypothesis that this statement from the start is true. It's basic principle of induction. Okay, notice that we have here 3 to the 3k plus 3 plus 3. So it makes 3 to the 3k plus 3 times another 3 to the 3. Okay, I'm going to write it out some more. We get 3 to the 3k plus 6 right here, minus 26k, minus 26 minus 27, I believe, is equal to 169L. All right, then we can factor out the power of 3 out of this to get something, this 3 to the power of 3n plus 3, which is in our induction hypothesis. We're going to write 3 to the 3k plus 3 times 3 to the third power, because this is simply the same thing. If we multiply it times 3 to the third power, we add the exponent of 3. And the same goes on. And so now we can use our favorite tool of substitution. What we took in this note, we can simply put it into our new expression. And we can see what happens from there. So let's put in, I guess, 169L and K here. We're going to have first 3 to the third power is 27. We multiply it times a 69L plus 26K plus 27. And still going minus our K's and some constants. Okay, let's keep going to show this is true. 27 times 169L, doesn't matter, we don't have to deal with it. It already is multiple of 169, so I'm just not going to factor it out. But this is useful to factor out. 27 times 26, K, note, is equal to 702K. Then again, plus 27 times 27, that's equal to 9 cubed actually, so 729. Then we have our constants, minus 26k minus 26 minus 27 is equal to 169L. And again, if we do the calculations, we notice something extremely nice. We get that, again, 27 times 169L, already a multiple of 169, as we know, is going to be added to 676K. We just subtract those two, and if we combine terms here, we also get 676 is equal to 169L. And in fact, if we move our L, it doesn't matter. This basically gets canceled here. It's already divisible by 169. Why bother to keep working with it? We get 676K plus 676, which is obviously divisible by 169. If we factor out 169, we get 4 times 4K plus 4. And that is, in fact, equal to 169 times some L, because 4K is always going to be an integer by our conditions. Then this is true. So therefore, we have proved the inductive hypothesis that this works for any k plus 1. And then, as induction works, this can go on like a chain forever upwards, proving it for all natural numbers. How nice is that? Thanks for watching.